So we're going to cover the topic of security, but this is not security in general. This is going to be specifically about the role of operating system in security. So this may be somewhat narrower in scope than other security courses that you take. All right. So we're going to look at how operating system plays a key role in ensuring the security of a computer system. But also we will look at some concepts of access control and some of the concepts that you won't traditionally encounter in other settings. So so this picture here, if you're wondering or if you already figured out, this picture here shows an interesting principle of maintaining access. So as you can see in this figure, there is a parking lot, and access to the parking lot is guarded by a gate, right? So only people who have the access pass are supposed to go into the parking lot. If you see the tire marks on the snow around the gate, it seems like people who don't have access, they can simply drive around the gate and get back to the parking lot anyway, right? So so this basically shows that it's not enough to just one second, let me admit people here. Yeah, so this picture shows here that it's not enough to simply put a gate sort of access control mechanism. You should also make sure that there are no other ways to get access to a particular resource, right? So like suppose your house just had a door but no walls, so anyone could, if your door was locked, it's no good because people could get in through other ways. So which is surprisingly common in computer systems. So so I'm going to move forward. So we're going to first broadly define computer security, and this is something you might have encountered in other settings as well. Security means CIA, and that's not Central Intelligence Agency. It stands for confidentiality, integrity, and availability. So, so confidentiality means that if you have some sensitive data, you don't want it to be exposed to people who are not supposed to have it, right? Only people who are supposed to know a particular piece of information should have access to it. Integrity means that no one should be able to tamper with the data if they don't have the correct authorization. And availability means that any system that handles your critical information or provides you critical services, these should not be subject to denial of service attacks. People should not be able to prevent you from being able to access your services. So let me see. Anyone having problems with screen blinking? Sagar says his screen is blinking for some reason. Okay, nope. I'm sorry, I don't know what's going on, but maybe you could turn off the video, turn it on, or try to rejoin the classroom. It might solve your problem, okay? All right. So, keeping any security. So the security definition pretty much captures any threat that you can think of and any solution that would address the corresponding threat. So we're going to take a little more broad view from OS perspective to see what kind of how do we get the CIA is all very nice in concept, but what does it mean as far as OS is concerned? So usually we want to we think about security as a threat model. Like, what are we protecting against whom? Who is trusted and who is not trusted? So one way to look at security is to say that OS is a critical piece of software which controls all the hardware resources, so we don't want OS to be compromised, right? And then the users are untrusted, and as a result, we want to protect the operating system from untrusted users. So for this, operating system can implement mechanisms that prevent users from gaining access to operating systems data and memory and code and so forth. So the other way to look at it is that users are being provided some service, and one of the services is isolation. So you want to protect users from one another. And that might mean not just protecting the processes that they're running, but also their files on the disk, and implementing access control mechanisms in order to implement inter-user isolation. So, and finally, sometimes you might encounter that users also need to be protected from the operating system. For example, if you log into a virtual machine running on a cloud platform, you don't know who this cloud provider is, or how trustworthy they are, or whether the employees of the cloud platform are trustworthy. So if you're running some sensitive applications or handling some sensitive data, you want it to be protected from the underlying cloud infrastructure. So in such cases, you don't trust the operating system of the machine on which your applications are running. And this provides for an interesting threat model. Usually from a personal computing settings or in enterprise computing settings, you trust the OS. But in a public cloud setting, you don't trust the OS, you don't trust the infrastructure. Right? And there's also another threat model not mentioned here, which is the hardware. So usually we trust the hardware of your computer. We trust the CPU, we trust memory, all the IO devices attached to it. But sometimes the hardware components can be malicious, and they might try to compromise the applications that are running in the computer. So again, that's a harder threat model to defend against, but there are lots of people who look into these kind of threat models. Okay. So any questions so far? All right. So we have looked at many security mechanisms already. Actually, the key role of operating system is to maintain system security. And we have looked at it from the CPU, memory, and file system levels. At the CPU execution privilege level, we have looked at privilege rings. For example, in x86 platform, whenever the OS code is running or the user code is running, the CPU has an E-flag register which stores the current execution privilege of the code. So if the OS is running, the execution privilege is 0, and if the user space programs are running, it's 3, and you can use these intermediate privilege rings. In addition, we have seen in virtualization that if you're running virtual machines, then there's an orthogonal privilege mode called root mode and non-root mode, which is different from your root user that you see in Unix systems. So these are hardware privilege levels. So root mode is where the hypervisor and its code runs, whereas the non-root mode is where the virtual machine and all its application and OS run. Right? And within root mode and non-root mode, you can have levels 0, 1, 2, and 3. So then there is in terms of memory, we have seen various privilege mechanisms. So we remember when we talked about virtual memory, we said there are two main roles of virtual memory: relocation and protection. So relocation means that you have a virtual address, then it might correspond to some other physical address in the physical address space. So, but then the protection part is that when a process accesses a particular page in memory, is it allowed to do that access? So for that, in page table entries, we saw that there are read, write, and execute permission bits. Plus, in addition, there is a user versus OS or supervisor bit for every page. So if a process wants to access a particular memory, then the MMU will first check whether the process has the corresponding access permissions, and that before it allows the access to go through. So, and likewise, if you have reviewed the lecture on segmentation, you would have noticed that in segment descriptors, there are two additional bits that describe the privilege level with which a particular segment can be accessed. So, so those two bits correspond to, at least on the x86 platform, they correspond to these four privilege levels 0, 1, 2, and 3. So, so basically, the access to a particular memory region would depend upon the contents of the permissions in the page table entry, the permissions described in the segment descriptors, and the CPU privilege level specified in the E-flags register. So for example, if operating system is accessing its memory, then the page table entry bit, protection bit would be 0. The segment descriptors, the 2 bits would be 0, 0. And the E-flags would say that the process currently running on the CPU has privilege level 0. And likewise, if a user space process is running, then page table register entry would be 1, page table entry would be 1, segment descriptor would be 1, 1, which corresponds to 3, and E-flags register should be 3. So these three components should match each other, the privilege levels should match each other in order for memory access to go through. Of course, I've simplified this description. There are many different combinations with complex set of rules that the MMU would validate upon every memory access before memory access goes through. All right. And finally, at the file system level, we have persistent data that's stored on the disk, and the operating system or wherever the file system implementation exists would have some authentication mechanism for every user process that executes. The permissions for that process would be matched with the user account and access permissions on the disk that are stored in the inode, and or what we call the metadata for each file before a file access is allowed, right? And there are many different types of access permission. We looked at a simple access permission mechanism called discretionary access control, where each file in Unix has user group and other permissions, right? And for user group and others, you have read, write, and executable permissions. So when you do an ls-l on a Unix system, you get to see this discretionary access permissions. So, but there are more complex access control mechanisms, and we'll cover some of these later in the lecture. Okay, so there's a question here. You mentioned hardware threat model earlier. What is the threat model actually? Well, the model there was basically that you don't trust the hardware on which your applications are running. So for example, somebody comes in and plugs in a USB drive, external USB drive. It might contain a virus and it might infect your computer, right? Or they can have more sophisticated threat models where there might be some hidden coprocessor that's constantly monitoring your memory contents and stealing SSH keys and so forth. Or there are side channel attacks where there may be hardware side channels that can be exploited by a malicious third party. So then, what do you do when you don't trust the hardware on which you're executing? Then you have to design your software in a different manner to be resistant to those kind of attacks. right? Does that make sense? Okay. So this is, again, you're all familiar with it. Why would anyone want to hack a machine? you know, and sometimes you just poke around and say, oh, I have some access to some files. Let me see what's in there, right? And then you can have insider threats. You fire an employee, but then the employee wants to take revenge. So as a result, they might, you can delete your files before they leave. And it happens more often than people realize. So extortion, people want to make money. This has become especially a big problem recently. What they there's the ransomware attacks where people hack into computers of hospitals or banks or whatever, or businesses, and they say, if you don't give us, we encrypt your files, and then if you don't give us money, then we are not going to give you back your files. So of course, governments do espionage, spies, and hacktivism. People might hack for social causes, and then there may be a whole bunch of a combination of these different reasons. So, for example, this is one example we might visit throughout this lecture, where Edward Snowden, if any of you remembers, he was a defense contractor, NSA contractor, a National Security Agency contractor, and he had access to pretty much the highest level of data. And what he did, he copied all the data on a hard disk and walked out of a NSA building in Hawaii, and then he took a flight all the way to Hong Kong and ended up in Russia. Right? So why did he do it? According to him, he did it for a social cause. He wanted to expose the government's wrongdoing. But some people did believe that he did it for espionage, which is he was possibly a spy because he ended up in Russia, right? But it was also an insider threat. Maybe he wasn't happy with his bosses, employers. So lots of different possible motivations, and nobody knows why he did it, but that's just an example to use. Okay. Any questions so far? Again, this has nothing specifically to do with OS, but just to keep some background in mind. Okay. So in any of these security mechanisms, whether you're trying to implement confidentiality, integrity, or availability, you need user authentication mechanism. If users are trying to access a system, you want to verify that the user is who they claim they are. So what that means is that if a user, very simply, when you log into your account, usually you might have to authenticate yourself by entering your user ID and password. And the system verifies that password match. The assumption is that only you know your password and nobody else knows it. So you must be who you claim you are. That assumption may break, but generally, that's a simple way of authenticating somebody. So something a user knows, for example, a password, or a security question, for example, like your mother's maiden name, or something a user has, something you physically heard. Like we all go to a shop, we use credit cards, and we swipe a credit card because we have the credit card. It is assumed that we are the owner of that credit account. Right? Or there's something a user has, for example, this has to do with biometrics, facial recognition, or fingerprint, and so forth. So, and authentication has to be done before a user is allowed to use the system. And what that means is that, you know, it's not that you're allowed to log in and then, by the way, oh, let me check who you are. Your authenticity has to be, your identity has to be checked before you are allowed to use the system. And sometimes there's continuous authentication where not only when you enter the system, but also as you're using the system. For example, some people monitor the pattern of keystrokes, right? And these systems, because every person has a different way of typing. And if you can recognize the pattern of keystroke, you can do continuous authentication as the user is using the system. Okay, any questions so far or any comments? Okay, so again, we'll go through very simple examples that you may already know. Passwords, something the user knows. So here's an example which shows that you have the example A, where you have the user enters the login ID, password, and then it says, all right, successful login. But then that's a successful login case. But then here's an example. This is an unsuccessful login. But you might notice that the user entered a username and it said invalid login name. And it might seem like, you know, very innocuous, but this is actually dangerous because whoever was trying to log in was obviously not an authorized user, and you're given some information away that this user doesn't exist on the system, right? So which, and if somebody is able to probe the system sufficiently, they can get a pretty well-defined set of, you know, who are the actual authorized users in the system, which can be useful for attackers. So, and then the third example is what you might want a well-behaved system to do, which is that you provide the username, and then even though the user doesn't exist, you ask for a password, right? And then you say invalid login. So at this point, you know, if this is a malicious user, they don't know whether the login was rejected because the user was invalid or the password was invalid, right? So this is a little more tight in terms of information leakage. Okay. So storing passwords, of course, in old times, when somebody enters a password, you have to verify the password against an existing stored password. But in original Unix system, for example, the password used to be in a plain text file, and that file was only accessible by the root user. So the assumption there was that as long as the root user account is secure, then nobody can access the password, right? But then if the root user account gets hacked, then all the user accounts get hacked. Or if the system administrator is not, usually system administrator is a person, and if you don't trust your system administrator, then they might be able to read your password, which might contain private data. For example, if people are using their girlfriend or boyfriend's name or you know, some other sensitive information as their password, then, you know, it's visible to the system administrator. So for various reasons, storing plain text password in plain text is not a brilliant idea. So as a result, you know, people came up with one-way functions, one-way hash functions. So what that means is that if you think of your password as input X, then you send the password through a one-way hash value, hash function F, and as a result, you will get a value Y, right? And this value Y is what will be stored in a file, in a password file somewhere in the system. So so later when a user tries to log in and they input their password X, it goes through this function F, and you get a hash value Y. And this hash value Y is compared against a stored hash value to see if they match. The assumption is that, you know, if there are very few collisions in the hash function, then the the hash values will match only for that specific user, and as a result, you can allow the user to get in. But another property is that if somebody knows the hash value, let's say the password file gets stolen, it's full of hash values of all the users' passwords. So it is computationally infeasible to compute the inverse function of f. What that means is you can't guess what was the original password by just looking at the hash value. Of course, if you had enough computation power, like for example, you have a supercomputer, then you can run the hash function through enough input values and then do some brute force attacks and so forth. Or you could kind of compute the inverse function as well from the hash value. But it needs non-trivial amount of computation. So for most practical purposes, for most ordinary systems, this is one-way hash functions are extensively used. Where of course, as computation power becomes cheaper, this becomes more and more insecure. Okay, any questions so far? All right, so let's keep going. Another approach is challenge response authentication. Somebody forgets their password, we all go through this CAPTCHA mechanism, right? But another way is using security questions. Sometimes you have to answer some additional questions like what is your mother's maiden name, where were you born, and so forth. Only information that only you're supposed to know. But of course, it's with we are living in information age. Everything is just a Google search away. So and these can also be easily guessed by getting information from multiple sources. So, so for example, if some website asks me, what is your mother's maiden name or where were you born, I wouldn't give the real answer that people can find on the internet. Instead, I would make up an answer and then provide that answer that only I know what the answer is. So you don't have to give a real answer to these questions. Just something to keep in mind. Also, you might be asked to compute something that only humans can compute, for example, just to avoid automated systems from trying to hack into these authentication mechanisms. So you compute the nth prime number and so forth, right? Or add two numbers and so on. So of course, if you forget your password and you can beg there may be like a customer service number, for example, and you can beg the customer service, call up the customer service and try to convince them that you're the correct user. And oftentimes it works. Unfortunately, there have been some high-profile cases. If any of you followed the news a few years back, the previous CIA director, John Brennan, he had a Yahoo email account, and somebody hacked into his Yahoo email account. The way they did it was by simply calling up Verizon, which owned Yahoo, and then convincing them that they were John Brennan and they'd forgotten, and then finally customer service let them access the account. So that was pretty awesome, I thought, for a CIA director to lose control over his account. And of course, there have been other. So we had a vice presidential candidate, Sarah Palin, who lost access to her account in a similar manner. And that was, again, it related to poor choice of security questions, right? Everyone knew she was from Alaska and who her family members were. So, so just to give you some idea that every authentication mechanism has some assumptions built in, and if you can attack those assumptions, then those become the weak points, and you can compromise the underlying mechanism. Okay, and here's you could, instead of relying on something the user knows, you can rely on something the user has, something physical. So for example, people, when you get into a lab, you have to swipe your ID card to get into the lab. So that's a physical object-based mechanism. Likewise, if you're trying to use a computer, then you might, there may be smart card reader somewhere in the computer that you have to use in order to get access. So, and these days, we all do two-factor authentication where when you try to log in, your password is not in, or a text message is sent to you on your phone, and the assumption is that only you have your phone and only you can read your messages. So that that way you're able to, and you not only enter your password, but also a code that you get through the text message. And it seems to work fairly well, but sometimes you can lose control of the physical object, right? Somebody else gets your ID card, they can use it to walk into the building and steal things. And another novel attack these days is, with two-factor authentication, they can steal your phone number. Even though they may not steal your phone, they can steal your phone number. How do they do that? Well, people allow you to transfer, these phone companies allow you to transfer your phone number. So someone can call up the phone company and convince them that they're trying to transfer your phone number, and phone companies don't have a very strong security mechanism around this process, at least a few months back. The owner or CEO of Twitter had his phone number transferred without his knowledge, and somebody hacked into his own Twitter account, which was pretty embarrassing. So after that, I think Twitter stopped using two-factor authentication for their account. So again, having a physical object is also not foolproof. If you can attack the assumptions built into the mechanism, you can compromise the system. Okay. And biometrics are supposedly harder to fake because it's something who you are, user's body. For example, your voice, your face, fingerprint, and so forth are unique to you as a person. But the problem with it is that the recognition mechanisms have to deal with multiple dimensions of features, and there is no hard science, foolproof way of making a match. So, for example, two people's voices may be similar. There may be false positives or false negatives, and people false negative means that someone needs to have an access to a system. They are a valid user, but then the face recognition system doesn't recognize them. Or if you're using fingerprint on your phone, for example, oftentimes the phone may not recognize your fingerprint because your finger is dirty or something. So these are not perfect mechanisms. And again, if the biometric mechanism doesn't work, then there has to be a fallback mechanism, such as a password-based mechanism or a two-factor authentication mechanism, and so forth. And they're also susceptible to spoofing attacks. This is there was a very funny example where we have a faculty in ECE, Scott Craver. He took like a very publicly available face recognition library, and then he tricked that library to believe that he is Barack Obama. He just put like a striped piece of paper on his forehead. He stuck it on his forehead, and then it did a match against an existing database, and it showed, oh, you're Barack Obama. So it's just funny. So some of these systems are very easy to fool. And of course, there have been other examples too. If you search on the internet, you might find some interesting examples. So biometrics are often thought to be very secure, but actually they are not a foolproof way of providing authentication. All right. And then, of course, you can have countermeasures for example, common example is you try to log into a system many times, and then if there are too many invalid logins, then it might prevent you from logging in, or you're trying to log into a system at a strange time, like 2 a.m., whereas you usually log in from 9 a.m. to 5 p.m. Or you log in from somewhere in Eastern Europe instead of Binghamton, New York, then that might be a trigger. So we talked about two-factor authentication. Another countermeasure and rather important defense is logging. So what logging does is it keeps track of all the critical events in the system and it records them, so that if something goes wrong, then you can go back and do a trace to find out what set of events led to a breach in your system. So for example, we all log into Gmail, for example, and it will tell us, okay, where was the last login from, somewhere on the screen, right? And if you don't recognize it, then you can do things to secure your account. CAPTCHA, we all have to click on figures to identify, do you see red light, or do you see trucks, or do you see bicycles? And we all play that game when we try to log into various websites. Another countermeasure is to have honeypot accounts. What that means is to create fake accounts that only that don't belong to real users, and someone tries to successfully logs into those accounts, it means that they're possibly a malicious user. So, and then you can monitor their behavior and do some back tracing to find out who they are and try to possibly catch the intruder. All right. So this is all common knowledge. Again, we are dealing with a high-level view of security here. Any questions so far? Any comments? Any experience you want to share? Okay. So we're going to look a little more at these attacks and countermeasures. Trojan horses are, usually someone tries to inject a malware or a virus into your system using something else that looks innocuous. For example, email attachments. Someone may send you an email attachment, and if you open that email attachment, your system is compromised because it executes some malicious code, right? The countermeasure, CM stands for countermeasure. You can either don't open, you can open an attachment in a virtual machine. If the virtual machine gets compromised, you can throw it away. Or you can have a cloud-based platform to open your attachment, so that if anything bad happens, it happens in the cloud, not on your local machine. So people may set up malicious websites that have JavaScript code that attacks your computer and hacks it. Or they might have Flash plugins that might be vulnerable, right? So again, you can disable JavaScript or disable Flash plugin, but you also lose functionality when you do that. Oftentimes, programs that are supposedly free are not necessarily free. They can they can have code to track you or monitor you. They can, compromise your system. So again, you can run things in a virtual machine, and sometimes, these virtual machines can lie about the environment. For example, if the code is trying to find out, what's your operating system version and so on. If you run in a VM, the VM can lie about the OS version that it's running. So, so some of the ways to protect your identity, right? And then another way is that people often use some common tools in their computers, and if a hacker can replace those programs with their own hacked version of the program, then that's again a Trojan horse. You're tricking a user into running a program that they think is legitimate, but they're actually running a malicious version of it. So again, this largely depends upon the system administrator. If administrator can strictly control file access permissions and prevent such modification, then you may be able to protect your system against these attacks. Okay, any questions so far? Very quiet class. Okay, let's keep going. So I'm going to skip talking about these viruses and worms. Everybody knows what viruses are, not the COVID-19 virus that we're talking about. Although I won't be surprised if we get a digital version of that very soon, right? But viruses are specific to a single machine, but worms can spread from one machine to another over the internet. So again, this is somewhat OS related, and the idea is that you go to a public computer lab or let's say an internet cafe, or you go to some website that looks like a legitimate website, right? Let's forget the website part. That's a different problem. So here, you go to a computer and presents you with a login screen. Let's say you go to one of the pods, and then you type your username and you type your password very carefully, and you typed it correctly, and you press enter, and it says, sorry, password unrecognized, and then it gives you another login prompt, and you try again. You think you've made a mistake, so you try again, and this time you're able to log in. So what just happened is possibly that somebody swiped your login credentials. So the screen that you saw the first time was a fake screen, and as a result, the first time they stole your password, and then they gave you the real login screen in which you logged in again. So they look the same, the fake screen and fake login screen and the real login prompt, they look the same. So there's no way for a user to tell, right? But then the only difference against it is for the user to be aware that such an attack can happen. Okay? So, so one of the common techniques, and this is usually in Windows operating system, if you go to a Windows computer in a public lab, and say press Ctrl or Del to log in, right? So what does that mean? So Control or Del, it kind of feels strange. Why should I press Control or Delete to log in? I mean, usually you do Control or Delete to reboot the computer. Why do you have to use that to log in? It turns out that Control or Del is what is known as, it gives you access to what's known as a trusted path. Trusted path means that this key sequence, Control or Del, is directly intercepted by the operating system. It is never sent to a user space program for processing. So when you press Control or Del, then you get a login screen. You can trust that login screen that it comes from the OS and not from some fake hacker who's trying to swipe your password, right? So it sounds kind of pretty cool, that here is a key sequence that will give me access, that will allow me to talk to the OS directly and not have someone else sitting in between, a man in the middle, right? But of course, this depends upon the user knowing this concept of a trusted path, to understanding that Control or Del gives you access to the OS. Most users, ordinary users, don't know, why am I being asked to press Control or Del? Somebody walks into a computer screen and they see a phony login screen that looks like a legitimate login screen, and let's say they don't know they have to press Ctrl or Alt Del, and they might just go ahead and enter their password anyway. So it doesn't serve the purpose that it's supposed to serve. So the other thing you could do is that you could actually, the first time you could enter a fake password, so that if someone is trying to swipe your password, they might not get it. And then the next time around, you enter your real password. Okay. So, but another example of social engineering. All right, so logic bombs, again, I won't go over it too much, but it has to do with insider threat. Employees, they don't try this. If you're not happy with your employer, don't try this at work. You might get caught, but of course it's also a bad thing to do. That people set up a logic bomb and then they get fired and then they leave, and then possibly set up such that if you don't enter your password for a while, then it destroys the employer's data and all that stuff. But possibly the employers are also smart, and they log all the activity. And so this apparently happened recently at Tesla, not recently, a couple of years ago. So this was in the news, where Tesla fired an engineer, and before leaving, he had set up a logic bomb, and after he was fired, it pretty much destroyed a whole lot of critical data for Tesla. It took them a while to recover from all that information. So, so there are some high-profile examples, but of course, there are other cases too where this might happen. Okay. Questions so far? All right. So I'm going to skip buffer overflow because you can again, it's not OS specific, but you enter an input is larger than the size of the array, and then it overflows and overwrites the stack. And you can change the return address and change the control flow. So there are many other places you can learn about buffer overflow. So let me quickly, all right, so this is somewhat OS related. So memory reuse is very interesting. Let's say you do a malloc operation, you get a piece of memory, right? Now, you might, again, I'm simplifying the example a little bit for this sake of concept, but you get this memory page and you can say, well, let me see what's in that page before I write anything into it. Okay, so you can just scan the contents of the page and see. But that page that you just got, it might belong to some other user, right? So maybe that user left behind some interesting information like a password or SSH keys or emails and so forth. And if you have a program that simply allocates a piece of memory and then scans it for personal information of other users, it might very well succeed. And apparently such kind of attacks have been demonstrated in, for example, cloud platforms. Somebody did it for virtual machines. They had their VM running besides other VMs, and they could read other people's SSH keys and emails and so forth. So, and they published a paper about it. So, and this is called dumpster diving, not driving. What that means is that you just like you go through a dumpster to see if you find some interesting somebody's credit card statement that you can use their credit card number. So this is the digital equivalent of dumpster diving. So of course the solution is fairly simple, that when we free a piece of memory, we give it back to the OS, not as in using free system call. Let's say a process dies and then its memory goes back to the OS. Most operating systems won't scrub the memory. Scrub meaning to write zeros into the memory or write some random values into the memory. Most operating systems will just take the memory, put it in the free memory pool. Then when somebody asks, some other process asks for memory, they'll take a page out of the free memory pool and give it. So if you had some sensitive data in that piece of memory that your process gave up, it might end up in the hands of another process, right? So And if that other process is curious enough, it can read all your sensitive information. And this may not be a problem on your personal computer, but this is a huge problem. Actually, it can be a problem even in your personal computer. We'll come to that in a bit. But it's also a huge problem in cloud platforms where many untrusting users are running their applications side by side. Okay. So what we're going to do, of course, we can modify the operating system to ask it to scrub. So every time someone frees a piece of memory, the OS can go and write zeros in the memory before it allocates it to somebody else. The problem, why don't operating systems do it? Well, because it's expensive. Because memory is being freed all the time. And if the OS is writing zeros, writing to an entire page of memory is expensive. It takes up CPU time. And if you do it often enough, then it can add up. The cost can add up. So you want to do it only for really sensitive information. Like that some piece of memory contains credit card information. Then you want to scrub that memory. So, but OS doesn't know which of your memory pages contain sensitive information and which is innocuous, right? So as a result, the best defense is that your application should scrub it. So if you know that your data is sensitive in your own program, in your own process, before you make that free call or delete an object, if you're doing it before you delete an object, you write zeros into it, right? Of course, that's a problem with systems where the programs don't provide an explicit programming languages don't provide an explicit free operation, for example, garbage collection and so forth. Then what do you do? Well, then you have to somehow build some of your own scrubbing mechanism on top of whatever exists underneath. Okay, so it's just something to keep in mind. It's very interesting that OS doesn't zero out your memory. It will just take what you give it and then give it to somebody else, right? Right. Any questions so far? Okay. We talked about logging and to monitor system events. And one of the, of course, the more you log, the more information you have, the better view of the system activity you have, right? And the thing about logs is that you always append to the end of the log. So if a new event happens, you don't go back and update an existing event. You actually add a new event to the end of the log. Like when we talked about log structured file systems, right? Log always grows. But if you log too much, then it takes up storage space. Right? Logging is not for free. So logging takes up storage space, and logging also takes up extra time. Because whatever you're doing, you have to pause that activity in between to say, wait, before I execute an activity, like for example, before I let someone log into the system, before I authenticate someone, I'm going to record it in my log. So that adds some latency. So logging can take up storage, it can slow down normal operations, and it can add a lot of noise. If you're trying to find some critical events and you have a huge log with unnecessary events, then it can slow down analysis. Which events are important, which events are not important, and so forth. So, but then if you log too little information, then you might miss certain critical events, which may be important for your analysis. So there's a trade-off. How much do you log? How often do you log? So that you don't have so much logging overhead, but you still capture enough information. And sometimes logging can break privacy laws or users' perceived privacy. For example, we all go on social media like Facebook and we post stuff, right? But then behind the scenes, people are logging your activity, and then they're taking the data and then selling it to people. So your perceived, privacy is broken. Or telephone companies may be monitoring your phone calls, against existing laws. or the government may be monitoring your phone call, and that will be perfectly legal. So, so logging is also, has it's good for security, but bad for privacy. Okay, and that's another example where security and privacy are not the same thing. Sometimes they overlap, but sometimes there's a trade-off between security and privacy. Okay, any questions? Right. So, so some other ways to gain access to a system. You can, sometimes people do, probing of a system, like, there are some system calls, and then you can read the man page, and it says the system call should behave this way. And then you say, well, let me try it and see if it actually behaves. Sometimes the implementation of a particular mechanism doesn't match its specification, what the manual says how it should behave. And when there's a mismatch, that's an opportunity for a bad actor, a hacker, to get in, right? So sometimes you might read some instructions for a system, and it'll say, don't do this, or don't do XYZ. Or you're walking through a building, it says only authorized personnel beyond this point, but nobody is there preventing you from going in. So you say, hey, let me see what's in there. There must be something interesting. So, or you might do something like an insider attack to convince the programmer to add a backdoor to let you get into the system. So again, these are not some things you should, I'm not asking you to do these things, but you should be cognizant of the fact that, as a system designer, that these kind of threat models may exist, and how do you protect your system against these threat models. Okay. So these are some general design principles for security. Default should be no access or minimal access to get things done. Always, check for current authority. If you're performing some action, then check you have current authority to do so. For example, when you use the sudo command, the first time you use sudo, it asks you to enter your password, and then that authority stays for like a few minutes. But if you don't use the sudo command for a while, then the authority is taken away, and you have to re-authenticate yourself. Right? It'll ask for your password again. Giving the least possible privilege, no more privilege than is necessary to get your job done. The protection mechanisms have to be simple, uniform, and at the lowest layers of the system. So if mechanism is too complicated, then people won't follow it. They will try to find ways to get around it. So it should be, again, goes back to the simplicity part. It should be psychologically acceptable. And, if, for example, certain systems, they have a ridiculously complex password requirements, like you should have, 5 capital letters, 20 numbers, another 10 special characters, and so forth, and some minimum password. And of course, nobody is going to be able to remember a very complicated password. So what do? They write it down somewhere. They put post-it note on their computer, which is worse than having a simple password that a user can remember. Okay. So we talked about containers earlier, and and of course VMs, and one of the common, we talked about FreeBSD jails, and the idea, one of the use cases there was using sandboxes. Sandboxes mean you take an untrusted code, you run it in a secure virtualized environment where the application from which your untrusted code cannot get out and hurt the outside world. So you can also think of your web browser as a sandbox. For example, you go to any website these days, there's JavaScript in the website, and that's code, untrusted code that's running, right? So if your web browser is well designed, it would sandbox the JavaScript so that it doesn't get out and do things with your system that it's not supposed to do. So, but then anytime you design a sandbox, of course, attackers will look for ways to get out of the sandbox. So for example, for virtual machines, people have demonstrated ways to do VM escapes where VMs gain hypervisor privileges, or jailbreaks for FreeBSD jails. For example, we talked about it last time where um, the supposedly sandbox code can get out of the sandbox. So you're going to spend a little time on access control in order to, and here OS plays a very critical role. Access control means that there's some resource that only certain users are expected to access, and the OS plays a central role in making sure that only those particular users can access and nobody else can. So there are many different types of access control mechanisms. There's discretionary access control, which is fairly common. For example, Unix implements discretionary access control. With discretionary access control, the idea is that it's called discretionary because the permissions associated with access permissions associated with a file or any resource are up to the system administrator's discretion. Whatever permission the system administrator sets, that's what the permission becomes, right? So if a system administrator, for example, forgets to protect certain critical files in the system, or they sets the wrong permissions by mistake, then the entire system becomes exposed, right? So as opposed to discretionary access control, there are mandatory access control systems where the access control mechanism is part of the system design. Right? Even if the system administrator wants to override access permissions for a particular resource, he or she can't do it. Okay, so this is particularly important in military or spy systems, national security infrastructure, and so forth. So we're going to spend some time on mandatory access control mechanisms. And then there are, in enterprise settings, you might have things like role-based access control, where your access permissions to a particular resource depend upon your role. For example, if you're a CEO, then you can access certain data, whereas if you're a software engineer or a secretary, then you can have more limited access, for example. And then, of course, there are takes on that, administrative role-based access control, which deals with who decides which roles can access which data. Right? So there are administrators who can say, well, the secretary can now access XYZ, or a faculty can access these students' records. So as opposed to discretionary access control mechanisms where access permissions are associated with individual users, here in role-based access control, the access permissions are associated with roles. The person who is the CEO or the department chair, they might change, but the access permissions don't change because the access permissions are associated with the role. Okay. So that's another example of one more layer of indirection to make things simpler. Okay, any questions? All right, so access control list. I won't go into too much detail here. Sometimes instead of having user group other permissions for each individual file, you might have an access control list which is a little bit more flexible. All right, so let me just skip this one so I can actually spend more time on the mandatory role-based access control. Okay, so it's OS at the very least what an OS should do. Remember when we talked about all the responsibilities for an OS, we looked at things like multiplexing and managing user state. But one of the key roles of the OS was managing access to resources, right? Protection of the hardware resources, of users from each other, and so forth. So if you take everything that an OS does, and you can kind of separate out all the various components that deal with security, then at the very core, you would find something called a reference monitor. So let me just point it out. So here, a reference monitor is where any access control mechanism is implemented. So whenever you access a particular resource, the part of the code, part of the OS that decides whether you have access to the resource or not, whether the access is allowed to go forward or not, that's called the reference monitor, right? And reference monitor is obviously really important because if your reference monitor is compromised, then the entire system is compromised. Of course, this picture shows one reference monitor. This actually, the reference monitor may be many different components all over the OS, right? But all of them taken together, you can think of it as a reference monitor. But in addition to that reference monitor, there may be other parts of the code that form what's called the trusted computing base. So trusted computing base means that if this trusted computing base again gets compromised, then your entire system is compromised, okay? So you rely on the trusted computing base to be implemented correctly and to be functioning correctly, because otherwise the entire system becomes vulnerable. So you notice that this is called trusted, and so what this kind of, if something is trusted, people get this nice warm and fuzzy feeling of security, that everything is secure. But actually, trust is a bad thing, right? So when I say that I trust a piece of software running on my computer to do the right thing, it doesn't mean that I have verified each and every line, I have checked every piece of code to know that it works correctly. Instead, it means that I trust the source, whoever wrote the code, whoever claims to have written the code, I trust them to have done things correctly so that I can build other stuff on top of it without worrying about security. So for example, we all rely on our operating systems. We trust on our operating systems, whether it's Linux or Windows or Mac, to be working correctly. So, but if the trusted computing base is not implemented correctly or it has bugs or vulnerabilities, then it's game over for us, right? So it's really important because trust implicitly means an assumption of security rather than verified security. It is important that this box, which says trusted computing base, be as small as possible, right? Because the larger the trusted computing base, it means there's more code in the system on whose correctness you rely in order for the security of your system. But if your trusted computing base is small, then it means that there's less chance of something going wrong, right? Of course, you can have a small piece of code and there may be one critical bug in that piece of code that can compromise your whole system. So having a small trusted computing base is not guaranteed to give you security, but it's more likely to be secure because hopefully programmers have had more chance. So for example, most modern operating systems have millions of lines of code, right? There is no human way possible that somebody has verified every single line of code and make sure that everything works correctly and securely with every other piece of code, OS. Okay, so modern monolithic operating systems are huge and they have a huge trusted computing base, so they're highly insecure. But then there are other operating systems where this trusted computing base is designed to be very small and sometimes formally verified to be secure, and everything else that belongs to the OS or everything in this white box is untrusted. What that means is even if these parts get compromised, it doesn't affect the security operation of the rest of the system. So I just want to emphasize this point that having a small trusted computing base is important. Having a large trusted computing base is not a good thing. Okay. Any questions? Okay. So coming to mandatory access control or multi-level security. So this is as opposed to the discretionary access control, where we want to now build security policies into the access control mechanism so that even a system administrator is not able to bypass it. Right? And this is really important in military systems and national security agencies and so forth. But then, because a lot of people who may not necessarily be technical have to deal with these systems also have to be very simple to understand for humans. And from the very beginning, they were designed to be very simple to understand. So multi-level security, MLS, is also known as mandatory access control. These are two names for the same thing, MAC or MLS. When you hear these terms, they mean the same thing. And the idea is very simple. And when I describe it, you say, why does it even need, such extensive research and so forth. So the idea is that you have some data objects that need to be protected, and these could be classified as top secret or secret or confidential, unclassified. So you can have various levels. That's why it's called multi-level security, right? And then sometimes people make additional subgroups or compartments within a particular level. For example, crypto subs, no foreign means no foreign, and so forth. And the meaning for each level is fairly well understood within the community, right? So of course, what that means is the data that's marked top secret is more sensitive than data that's marked secret, so fewer people should have access to it. So likewise, just like data objects, you have people, and people have clearances. So in order for someone to access a top secret data, their clearance should also be top secret. So people are also given clearances for top secret, secret, confidential, and so on. So it's fairly easy to understand. If I have only secret clearance, then I'm not allowed to access data that is top secret, right? Or if I have only unclassified clearance, then I don't have access to any of the data which is at a higher level. So it's very easy for people to understand. Okay, so what's all the fuss about? So if you think about how this is implemented, right? The implementation of this MLS mechanism. Now remember that it's not just people, but now also computers that are these entities. So in the previous slide, we have people, but also computers who might want to access and process this data. So both need classification, right? So so here in this picture, we look at these rectangles are entities, people or computers, and data is the data that you're trying to access. So in an MLS system, we have two principles: no read up and no write down. Right? So the first one is very intuitive to understand. So if there is some data at a high security level and there is an entity at a low security level, then this entity should not be able to read the data. This person or this computer should not be able to read a higher security level data. For example, an unclassified computer or unclassified person should not be able to read top secret data. Okay, and we'll get to write down in a minute. if you look at what's allowed, you're allowed to read down. What that means is that a person who has a higher security clearance can read data at a lower security clearance with a lower security label. Likewise, um, so now you'll see that write up is allowed, which is interesting. That there's a person with a lower security clearance, they're allowed to send data to a higher security clearance. They might have a piece of data and they can classify it as top secret, but once they do that, only people with top secret access can access it, right? So, for example, if you have spies in the field who are collecting information, and they might collect some information and they can mark it as top secret and then send it to a higher level. So write up is allowed, right? And likewise, you'll see that write down is disallowed, which is, what does that mean? It means that someone with a high security clearance is not allowed to pass data to a lower security level. Okay, so I can't take, although I may have clearance for top secret, I can't take a top secret data and give it to someone who has unclassified clearance, or I can't give it to a journalist, right? So what is that? If I take top secret data and give it to a journalist or some foreign enemy, then that's called leak, okay? So that's why the MLS implementation mechanism has to prevent the write down operation. And because even though you may have high security clearance, doesn't mean you're trusted. Everyone is inherently untrusted, right? So, and if we go back to Edward Snowden's incident that we talked about earlier in this class, what happened there? This was an NSS contractor with a top secret clearance, and he was able to take all this data, put it down in a hard disk. And now you can ask whether the hard disk has high security clearance or not, right? And then, and if that was allowed, if that was not a write down operation, then he was able to take those hard disks and walk out of the building past security guards, right, who didn't check his bags. And the moment he walked out of the building from a secure environment from a top secret environment to an unsecure environment and take the flight out, it was another write down operation, right? So again, what that particular incident showed was that anyone being able to steal top secret information and leak it out, that's a failure of this no write down policy, which means that it's not enough to implement no read up. You also have to ensure that the system has no read down policy, right? So it's somewhat counterintuitive, but having a high security clearance doesn't mean you're trusted. Okay, any questions, any comments? Okay, so, but of course, there's theory and there's practice. In practice, no write down that we just discussed is not always possible. Like, for example, you get some information from someone with a lower security clearance, you have to at least acknowledge to them that you got the information. So it turns out that acknowledgement operation itself can create a backdoor. For example, if I give you one acknowledgement, it means that there is no attack on Russia tomorrow. If there's 5 acknowledgements, then it means we are going to attack Russia tomorrow, right? So you can piggyback information on top of acknowledgements. But then acknowledgements are still important to ensure reliability of communication. So what some people did was, at one of the defense agencies, they came up with this idea of an MLS pump where you allow acknowledgements, but the bandwidth of that acknowledgement is so low that you can't pass any useful information through those acknowledgements. Plus, you can add things like add noise to make it, to avoid having any side channels there, or rather covert channels. So, So yeah, so that brings us to the end of this lecture. We saw the role of the operating system in enforcing security at various levels. We also took a broad view of various access control mechanisms and specifically looked at mandatory access control mechanism and the no read up and no write down policies. Okay.